Welcome to Module 3.2, where we'll dive into a cornerstone of Bitcoin's functionality and security, the UTXO model. UTXO stands for Unspent Transaction Outputs. But what does that really mean? Each Bitcoin transaction you make creates outputs, which are like digital coins. When these coins are not yet spent, they're known as UTXOs. Picture it this way. If you have a $20 bill and you need to pay $15, you don't rip off 3/4 of the paper bill. Instead, you would hand over the full bill and get a $5 bill back as change. Bitcoin works in a similar way, but digitally. When you send Bitcoin, you're essentially breaking up your bill, or UTXOs, and creating new ones, which are then distributed to the receiver and back to you as change. This mechanism gives Bitcoin an edge over traditional banking because every single UTXO is individually signed and verified, preventing double spending and providing robust security. Let's see the UTXO model in action through an example. Alice has received 3 Bitcoins in a previous transaction. Let's call it Transaction A. These 3 Bitcoins are currently recorded as a UTXO belonging to Alice. Now, Alice wants to send 1 Bitcoin to Bob. She initiates a new transaction, Transaction B, where the UTXO from Transaction A is the input. In Transaction B, Alice needs to create 2 outputs. The first output is 1 Bitcoin to Bob's address. However, Alice needs to account for the remaining 2 Bitcoins from her original 3 Bitcoin UTXO because the entire amount of the input must be accounted for in the UTXO model. To do this, Alice creates a second output that sends the remaining 2 Bitcoins, which is called change, back to herself. Before the transaction can be added to the blockchain, it has to be validated by the network. Bitcoin miners will check that the UTXO Alice is trying to spend actually exists and belongs to her, which they do by verifying her digital signature against the public key stored in the UTXO. They also make sure that the total value of inputs equals the total value of outputs, which is 3 Bitcoins as outlined in our example. If all checks pass, the transaction is considered valid, and miners will then include it in a new block, which is added to the blockchain. The UTXO Alice, used as an input, which is 3 Bitcoins, is now spent and can't be used again. The new UTXOs, including 1 Bitcoin to Bob and 2 Bitcoins as change to Alice, are now available to be spent in future transactions. The records of all UTXOs belonging to Alice and Bob are both updated after this transaction. As you can see in this example, once a UTXO is spent, it cannot be spent again, therefore preventing double spending. Each UTXO is also individually signed and verified, providing robust security that is essential for the trustworthiness of Bitcoin and other cryptocurrencies that use this model. While this might sound incredibly complex, it's important to note that this process is mostly automated by Bitcoin wallets. Users like Alice and Bob don't usually need to deal with the technical details of the process or create transactions A and B. They only need to specify the amount they want to send or receive. One of the implications of the UTXO model is that, unlike traditional banking systems, Bitcoin doesn't keep a balance associated with your account. Instead, the balance is derived by adding up the value of all UTXOs associated with your addresses. The UTXO model provides many benefits, and chief among them is security. Moreover, UTXOs provide a clear audit trail. Each UTXO carries with it the entire history of its ownership, offering complete transparency over transactions. UTXOs can be processed concurrently, which may result in faster transaction times compared to systems that process transactions account by account. Lastly, while the UTXO model provides transaction transparency, it can also enhance privacy compared to account-based models. In the UTXO model, change from transactions is often sent to new addresses, making it harder to link transactions to a single user. But the UTXO model has a few limitations. One of its main drawbacks is that it can lead to a huge and expansive database that grows continuously, as each UTXO needs to be tracked separately in the database until it is spent. This poses scalability challenges. Just imagine the size of a database that keeps all information of who has ever held each dollar bill throughout history. But there are ways to mitigate this challenge. For Bitcoin, techniques like segregated witness and Schnorr signatures are helping the network to scale. With SegWit, signature data is separated from transaction data, reducing the size of individual transactions. Schnorr signatures, on the other hand, allow multiple signatures to be aggregated into one, increasing efficiency when multiple inputs are involved. The UTXO model can be more complex for users to understand, and wallets also need to implement UTXO selection strategies for creating transactions, which can be complex. Poor selection strategies can lead to privacy loss or higher transaction fees. Despite these challenges, Bitcoin's UTXO model has influenced many other cryptocurrencies and blockchain projects. The UTXO model continues to shape ongoing debates and development efforts regarding Bitcoin's future and its scalability. In the next module, we'll take a deep dive into Bitcoin's tokenomics to understand how they help keep the Bitcoin network secure.